Most people think Google's success was about searching for keywords. They're wrong. The real secret, the one worth $25 billion, wasn't about what was on the page, but how the pages link to each other. Imagine the internet as a democracy. Every link from one page to another is a vote. But in this election, not all voters are created equal. The hard way, the way 99% of students think it works, is simply counting the votes. If page 3 has 3 links pointing to it, it should be the most important, right? But there's a catch. A link from a reputable source like Yahoo should carry more weight than a link from a random blog. A simple count fails because it treats all votes as identical. This leads us to a self-referential realization. A page is important if it's linked to by other important pages. We define the score of page K as the sum of the scores of its backlinks, divided by how many links they give out. Let's look at our 4-page web again. For page 1, its score is the score of page 3 plus half the score of page 4, because page 4 splits its vote between 2 pages. If we write this out for every page, we don't just have algebra, we have a linear system. We can pack all these voting rules into a single link matrix, which we'll call A. Now, look closely. Our goal is to find a vector x that stays exactly the same after being multiplied by the matrix. In math, this is the eigenvector problem, a x equals lambda x. But why must lambda be 1? Think about it. If lambda were 2, the total importance of the web would double every step, exploding to infinity. If lambda were a half, the importance would decay, eventually vanishing to 0. For the web to be stable, where votes are neither created nor destroyed, lambda must be exactly 1. For this to work, the columns of our matrix must sum to 1. This is what we call a column stochastic matrix. It ensures that the total amount of importance in the system is conserved. When we solve for the eigenvector of our 4-page web, we get a clear ranking. Page 1 wins with 38% of the importance, even though it didn't have the most links. But there's a massive problem. The internet isn't one big happy network. What happens if the web is broken into isolated islands? In a disconnected web, our matrix becomes block diagonal. Now, we don't have one unique eigenvector, we have many. And then there are dangling nodes, pages that link to nothing. They act like black holes, sucking the importance out of the system until every page has a score of 0. To fix the broken islands, Bryan and Page force the web to be fully connected. They mix the original links, A, with a teleportation matrix, S, where every page links to every other page. Think of it as a random surfer. Most of the time, they follow a real link, but 15% of the time, they get bored and teleport to a random page. This creates invisible bridges between the islands. Mathematically, this means our matrix M has no zeros. Every page is connected to every other page. This positivity guarantees a unique ranking, invoking the Perrin-Frobenius theorem. This theorem guarantees that there is exactly one eigenvector with a positive score for every page. No matter how messy the internet gets, Google's math will always find a unique answer. But how do you calculate an eigenvector for a matrix with 8 billion rows? You can't use standard methods. You use the power method. You start with a guess. Maybe every page is equally important. Then, you multiply that guess by your matrix over and over. With each step, the error shrinks. The vector feels out the structure of the web until it settles into its stable state. Google doesn't actually multiply the big matrix M, they use a trick. They multiply by the sparse matrix, A, and then add a tiny bit of the teleportation value. This is why linear algebra is the backbone of the modern world. It took a chaotic, disconnected mess and turned it into an ordered, ranked reality. So the next time you search for something, remember, you're not just looking at a web page, you're looking at the entries of a $25 billion eigenvector. Calculus is the study of change, but linear algebra is the study of connection. And in the 21st century, connection is everything. Thanks for watching.